lecture has to do with molecular structure. And when we think about structure or molecular geometry, one of the things to keep in mind is many molecular properties can be explained by their geometry. Right? This idea that structure predicts reactivity. If we know something about the shape of a molecule, we know something about its polarity, its boiling point, its solubility, reactivity, how it might interact with enzymes in our body. So this idea that structure predicts reactivity is really crucial, and this is our start of understanding of what does a molecule look like, what is its shape. And the model we're going to use to explain is what's known as the valence shell electron pair repulsion, or VSEPR model. This is a really good predictor of molecular shape, and the main idea is that a molecule is going to adopt a shape where the electrons, either in bonds, covalent bonds, or lone pairs, are all negatively charged, and they're all going to repel each other. So the shape that a molecule is going to take is going to be the one that's going to maximize the distance between electron pairs or electron groups, right, and minimize the energy. Whenever we determine molecular shape, we always have to start with the Lewis structure. You have to have the correct Lewis structure before we can analyze and determine the molecular geometry. And the other thing to take note is we need to be thinking in 3 dimensions. What is the maximum space between electron pairs? And we have to be able to think in 3 dimensions. And that can be hard as we're drawing everything in 2 dimensions on paper. So how do we describe the electrons involved in bonding? And when we think about this VSEPR, valence shell electron pair repulsion, molecules are going to adopt the geometry that minimizes electron repulsion. Electron pairs are larger than covalent bonds. And what I mean by that is if you have a lone pair of electrons, that's actually going to take up more space than a covalent bond, because the electrons in a covalent bond are constrained between 2 atoms, and a lone pair is only associated with 1 atom. If you have a multiple bond, a double bond, a triple bond, these are counted as a single electron group. So as we see, we're going to start to count how many electron groups come out from a point. And a lone pair, a covalent bond, a double bond, a triple bond, each of those would count as 1 electron group. And we can then refer to what's known as the electron group number, or sometimes you'll see it referred to as the steric number. This is the number of atoms bonded to a central atom plus the number of lone pairs of electrons on the central atom. So another way of thinking about this is just how many things come out of a central atom. So if we count lone pairs, single bonds, and double bonds, each as 1 thing, how many things come out from the center? So then we can define what's known as the electron group geometry. And this is the 3-dimensional description of the arrangement of electron groups that come out of a central atom. And we're going to differentiate that from the molecular geometry. And the main difference here is the molecular geometry only concerns itself with the arrangement of atoms. So the molecular geometry and the electron group geometry will always be the same if there are no lone pairs. Once you have a lone pair of electrons, the electron group and the molecular geometry will be different. And so what I started off to do to illustrate this, since we can't meet in person and have models, I used this website from this PhET simulation, and this is what you'll be using in your lab as well. And I'm just going to walk through building some of these geometries so we can think about what they're going to look like in 3Ds, and also you get to see this simulation. So let's start the simulation. What we have is a central atom in purple and an outer atom in gray, and currently there's just 2 atoms with 1 covalent bond associated with it. So let's go ahead and start the simulation, and we can move it all around, we can drag it one way or the other. And so what I can do is, you can see what I just did is I added a second atom. And once you added the second atom, you can see these 2 electron groups, 1, 2, want to be as far away from each other as possible. And the furthest they can be apart from each other is this 180 degrees. And so I can move it all around, and you can start to click show bond angles 180 degrees apart. They're maximizing their distance. I can click show the molecular geometry and the electron group geometry. In this case, they're both linear. They're going to be the same because there's no lone pairs, right? We can see this is a linear molecule. All the molecules line up in a line, right? So what I'm going to do now is add a third covalent bond to that central atom and watch what happens to our geometry. So here we go. We add it and we can see how does this move, and we can move it all around, and the geometry that's going to maximize the distance between these now 3 electron groups is they all go out in sort of opposite directions. It ends up being 120 degrees apart from each other, and we can see down here at the bottom, the name of this geometry is trigonal planar, right? Because it forms a triangle and all of the atoms are in a plane. Okay, so we're going to go ahead and add a fourth covalent bond and watch what happens to the geometry as we add that fourth covalent bond. So if you notice, we can kind of do this again if you want, as we add that fourth covalent bond and watch what happens. All 3 outer atoms are in a plane. We add that fourth, and now we've destroyed the sort of plane of atoms. So this is when 4 things coming out of a central point, and this is a difficult one to see in 2 dimensions. The bond angle here is 109.5, maximizes the distance. The name of this geometry is called tetrahedral. All right, so 4 things coming out of a central point. The way we maximize the distance between those 2 things is a tetrahedral geometry with a bond angle of 109.5. So we go ahead and add a 5th covalent bond. Here's our 5th one, and we can add it. And we add our 5th one. One of the things you notice is we have this geometry. You can see down at the bottom, it's called trigonal bipyramidal. And in this case, one of the things to take away from this is you can start to see that there's actually 2 different positions here. So if I pause it right here, one you can see is called trigonal bipyramidal. Here's your triangle, 3 atoms all in a plane, 120 degrees apart, right? But if we kind of keep playing this and we twist it around, now you can start to see these bond angles are 90 degrees. So you have 2 different positions now. We have a top and a bottom, which we call axial, and we have 3 in the middle that form that trigonal plane that are called equatorial. And so we have 2 inequivalent positions in this geometry and 2 different bond angles. All right, so we can go ahead in a second, we'll add 1 more covalent bond to that central atom, and when we do that, we get what's known as the octahedral geometry. And in this case, we have a nice symmetrical molecule again. Bond angles everywhere are 90 degrees apart. All right, so this is the octahedral geometry. All right, so what we're going to do now is we're going to remove some of these bonds, and instead of having all covalent bonds, we're going to start to add some lone pairs. So we'll go back to tetrahedral, and here's our linear geometry, 2 things coming out, and now I'm going to add a lone pair. So now notice if I add 1 lone pair, here's my lone pair up top, I still have a 3 electron group geometry. So 3 things coming out. So my electron group geometry is still trigonal planar, 3 groups coming out. But notice my molecular geometry is different because the molecular geometry only has to do with the atoms. We sort of ignore the lone pairs, and so we call this bent with our molecular geometry. All right, so there's our bent geometry. We can go ahead and add a covalent bond. So now we have 3 covalent bonds and 1 lone pair. So again, 4 total things coming out. So that's a tetrahedral geometry or electron group geometry because 4 things coming out. And our molecular geometry is called trigonal pyramid. Trigonal pyramid because we form a triangle on the base. We can imagine this being the base of a pyramid and the central atom being the top of our pyramid. We can see again this trigonal pyramid molecular geometry. If we add another lone pair, notice now we have a trigonal bipyramidal electron group geometry, 5 things, right? And one of the interesting things to note is both of these electron pairs end up in what we call the equatorial positions because this is going to maximize the distance from those lone pairs, and the atoms that are left over are 90 degrees apart. So the molecular geometry we call T-shape because you form this nice T shape in the geometry. If we add one more covalent bond, so now we have an octahedral electron group, so 6 things, but 2 are lone pairs, and so now we have a square planar overall geometry. I'm going to back up now, go back to our linear molecule, and add now 2 lone pairs to this. All right, so if we have 2 lone pairs, now again we have this tetrahedral electron group geometry, but our bent overall molecular geometry. So I hope that it helps illustrate what these look like in 3 dimensions. Play around with this simulation. In lab, you'll get to play with it some more. We're going to sort of now draw some Lewis structures and apply that to the molecular geometry. So what I encourage you to do at this point is pause this video, and draw some Lewis structures. So draw all of these Lewis structures so you have them in front of you. And then what we're going to do is assign molecular geometries to each of these. And so the first one we're going to look at is BeH2, so beryllium dihydride. And if we draw this Lewis structure, we end up with an example of a linear molecule. So Be, 2 hydrogens coming out, so 2 electron groups. And the distance that's going to maximize these electron groups, or geometry, is a linear geometry, 180-degree bond angle, so they're as far apart as possible. The 3 electron group geometry, BH3, you can see a central boron, 3 hydrogens. So this is called trigonal planar because all 3 of these hydrogens are in the same plane. We can draw them all atoms in the plane of the paper. 120-degree angles maximizes the distance between each of those. Once we get to 4 electron groups, recall one of the things we saw was we can no longer put all of the atoms in the plane of the paper. And so we can draw a correct Lewis structure of CH4 methane. Right? This is a perfectly fine Lewis structure of methane. But what it does not do is help illustrate what does this molecule actually look like in 3 dimensions. And so remember what we said was this is a 3-dimensional molecule. We have a central atom. We have 2 of those carbon-hydrogen bonds are in the plane of the paper, and then one's coming out at you and one's going into the paper. And so this Lewis structure on the right is trying to illustrate this. So it's a tetrahedral geometry, and notice we have 2 covalent bonds that we're used to seeing, and then we have what we call a wedge and a hash. So if you ever see this wedge, all it means is it's a single bond, but it's trying to illustrate that this is coming out of the paper at you, and the hash is going into the paper away from you. It's attempting to draw this molecule in 3 dimensions. And that's what we're explaining here. So the wedge is coming out, the hash is going in. So when we can, we will try and represent molecules in their 3-dimensional structure by using this wedge and hash nomenclature. So we have 5 electron groups and 6 electron groups. So our 5 electron group geometries, we can see just on correct Lewis structure are shown here, but now we know we can better draw them with wedges and hashes. So our trigonal bipyramidal, we have 1, 2, 3 equatorial and 1, 2 axial bond angles of 120 and 90. And then we have for our octahedral geometry, we have all bond angles here are 90 degrees apart in a more symmetrical arrangement. So our electron group geometries, we have there's 2 groups, it's linear, 3 groups, trigonal planar, 4 groups, tetrahedral, 5 groups, trigonal bipyramidal, 6 groups, octahedral, just as we saw with our little video movie from the PhET simulation. Now, what happens when we have a lone pair instead of covalent bonds? Well, we saw this in our video, but just to rehash it, we can look at something like ammonia, so 3 covalent bonds and a lone pair. And so what we would do is say, this has 4 things coming out. So 1 lone pair, 3 bonds, that's 4 things. So the electron group geometry shows the arrangement of all electron groups. That's going to be tetrahedral. And the molecular geometry is only concerned with the atoms. And so here's our ammonia molecule drawn in 3 dimensions. 1 hydrogen comes out, 1 goes in, lone pair on top. We say the electron group geometry is tetrahedral because 4 things coming out. And the molecular geometry is trigonal pyramid. Again, your electron group and molecular geometry will always be different if you have lone pairs of electrons on the central atom. So now we can look at something like water. So water's molecular geometry is bent, right? Its electron group is tetrahedral, but overall we call it bent, and we can actually draw water all on the plane of a paper where you imagine 1 lone pair of electrons coming out, 1 lone pair of electrons going in. One further point I want to point out, if we look at something like methane, ammonia, and water, so methane, CH4, ammonia, NH3, and water, OH2. These all have electron group geometries of tetrahedral. The only difference is we're swapping out covalent bond for lone pair, and then another covalent bond for lone pair. So if we look at the bond angles of these, the tetrahedral, 109.5, the ammonia, 107, and water, 104.5. And what we're seeing is one of the things we started this lecture talking about. The lone pair of electrons take up more space than a covalent bond. So because this ammonia has a lone pair of electrons, it's actually going to push all of these covalent bonds a little bit further away from it. Water's got 2 lone pairs, and so it's going to start to smush these hydrogens down closer together and essentially scrunch them together. So this table sort of summarizes what we've kind of gone through. You can look at this, you can pause the slide and take notes of this. A couple common geometries, electron group geometries, and molecular geometries, lone pairs and bonding pairs. So these are the geometries that you should know. For this class, you should know the basic set of linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and then you should also understand the trigonal pyramid and the bent geometry coming out of the 4 electron group geometries. So I hope this helped get a basis of VSEPR theory, what it